Hello, I'm Desiree, and welcome to my presentation on using machine learning to predict power output. So the problem we're exploring is that power plants operate under varying environmental conditions, which significantly impact their power output. So predicting the power output accurately can help optimize operations and resource allocation. So the main goal is to develop a reliable model that predicts power output of a power plant based on environmental features to facilitate better operational planning and decision making. So the data set includes key features such as ambient temperature, exhaust, vacuum, ambient pressure, and relative humidity. So the target variable is the power output in megawatts. And the task type we'll be using is the regression problem because the target variable, which is power output, is continuous. The evaluation metrics we'll be using is the root mean squared error and is used to measure the average prediction error, while the R squared quantifies how well the model explains the variability in the data. So let me walk you through the steps I followed to build the model. So the steps I took for the machine learning model development process is one, to define the problem, which is to identify the type of machine learning task. And for this project, it's a regression task aimed at predicting power output based on environmental variables. Secondly, I chose the features most relevant to the target variable, which I explained on the previous slide, which is ambient temperature, because it directly impacts the efficiency of the generation. So higher temperatures can reduce engine performance due to decreased air density, while lower temperatures can improve efficiency. Then we have the exhaust vacuum. This reflects the effectiveness of the cooling system. Next, we have the ambient pressure. It determines the air density available for combustion. And then we have relative humidity, which influences the air-fuel mixture's density and combustion properties. So these features are critical as they influence power plant performance. Third step is to split the data. As I said, I used 80% of the data for training and 20% for testing. The testing set was used to teach the model the relationships between input features, for example, temperature and pressure, and the target power output. Whereas the test set, which was 20% of the data, was held back during training and used only after the model was built, providing an unbiased evaluation of its predictive accuracy. Fourth, I chose the algorithms. As I stated previously, I used linear regression and random forest regression for comparison. Linear regression was selected as a base model due to its simplicity and efficiency in modeling linear relationships. It provides a clear starting point for evaluating more complex models, whereas random forest regression was chosen for its robustness and ability to handle nonlinear relationships and interactions between features, making it well suited for data sets with complex patterns. Step 5 was to evaluate the models. I used cross-validation during training to compare the model performance across multiple subsets of the training data. So this approach ensured the evaluation is robust and reduced the risk of overfitting to a single train test split. And once again, to evaluate the performance, we use metrics such as the root mean squared error. In step 6, you select the best model. So I compared validation results and selected the model with the best performance. In my case, the random forest regression was chosen due to its lower RMSE value. And seventh and lastly is to evaluate on the test set. So the test set for this model that was held out was to calculate final performance metrics, the root mean squared error and the squared R, I'm sorry. So here's a bar chart of the results that I had from the linear regression, which had a root mean squared error of 4.57, and the random forest regression had a root mean square error of 3.47. And it was selected due to its superior performance. The lower that value, the better it was. So now let's evaluate the final model on the test set. So to assess the performance of the final model, I evaluated the random forest regression on the test set, which contained unseen data. This evaluation provided a reliable measure of how well the model generalizes to new real-world scenarios. So the results were we had a root mean squared error of 3.25. And this quantifies the average error between the predicted and the actual power output variables. As you can see with this small sample table that I have below, right, that a lower RMS indicates higher accuracy. And in this case, an RMSE of 3.5 means the model's predictions on average deviated only by 3.25 milliwatts from the actual power output. So this low error demonstrates the model's precision in predicting power output across varying environmental conditions. Whereas we have the R squared, which was at 0.964, indicating a strong fit because it's close to 1 indicates a strong fit, meaning less error. So when we look at the combination of a low RMSE and a high R squared demonstrates that the random forest regressor excels in this regression task. It not only predicts power output with minimal error, but also captures the underlying patterns in the data effectively, including complex nonlinear interactions among the features. And compared to linear regression, which had a higher RMSE and a lower R squared, the random forest regressor's ability to handle nonlinear relationships and interactions gives it a clear advantage, making it a better fit for this task. So overall, the results suggest that the random forest regressor can provide reliable predictions for power plant operations, enabling better planning, resource allocation, and operational efficiency. Understanding model results. So the key features that had the most impact or influence was the exhaust vacuum and the ambient temperature, whereas relative humidity had the least impact. And the implications of this is that this analysis helps prioritize data collection efforts by highlighting the variables that significantly influence the power output. By focusing on these critical features, power plant operators can optimize performance, make informed decisions, and allocate resources more efficiently to enhance operational efficiency and sustainability. So the forest rand's ability to capture nonlinear relationships contributed to its better performance over linear regression. To wrap up, here are the key takeaways from the project. I successfully built and evaluated a machine learning model to predict power output. I compared models to select the best performer using cross-validation and test metrics. It was determined that the random forest regressor achieved the high accuracy and interpretability through feature importance. It had a root mean squared error of 3.25. So this model can support power plant operations by providing reliable predictions of power output under varying conditions. The limitations of this model's performance is limited by the data range it has to train on. So the next steps could possibly be, for future work, would involve exploring additional features or ensemble techniques for further improvement. So thank you for your time.